Welcome everybody to the second invited talk of the conference. It gives me great pleasure to introduce Professor Damien Stehlé. Damien is a professor in the Department of Computer Science at ENS Lyon. He received his PhD from University Nancy in 2005. He was a postdoc at the University of Sydney and then a CNRS researcher until 2012. He studies algorithmic and cryptographic aspects of Euclidean lattices and is a co-author of the Kyber encryption scheme and dilithium signature scheme, which have recently been selected by NIST for standardization. He's published over 50 papers in leading venues of cryptography and also won several awards like Best Paper Awards at flagship conferences like Eurocrypt and Asiacrypt. It's our honor to have him here. Please welcome our speaker.
Thank you, Shweta, for the introduction. So first, I'd like to thank the organizers, so both the program chairs and the general chairs. I had a very good week, both with the papers and the organization. So thanks to the chairs. Yeah, I'm going to give a talk on efficient lattice-based encryption. So first, so I didn't know how to start the talk last week. But then I got some help from the French president, so who tweeted like 10 days ago. So he was visiting Biden, and during this visit, so the tweet is in French, but the explanation is in English. During the visit, he had a first diplomatic post-quantum communication between France and the US, and so I was puzzled by this tweet, not only by the reference to matrix, which I found a bit odd, but so I wanted to know what was inside, what was used for this communication, and it turned out that it was using dilithium for signature and photochem for the encryption, and so I was just like, photochem, why photochem rather than Kyber? Why are you spending a factor 12? What is the underlying reason? And what came to my mind is, yeah, maybe they want to avoid algebraic lattices for some reason. But that also doesn't sound very consistent, because then why dilithium? So, which is also relying on algebraic lattices. So, so in particular for encryption, there have been conflicting messages about the use of algebraic lattices, and so yeah, I'd like to during this talk to have an overview of what is known in terms of security and assumptions. Okay, so I'm going to start with untrue, and then talk about ring LW and module LW constructions, and then I will wrap up with some open directions that I find interesting. Okay, so let me recall the algebraic setup. So we have two rings. So first there is a polynomial ring R, which is E of X modulo some integer polynomials, which is monic and irreducible. So it plays the same role as the integers. So you instead of integers, you take integer polynomials. And then there is a mod Q version of that ring, RQ, where Q is a small integer larger than 2, which is ZQ of X mod the same polynomial phi. And by default in this talk, I will use phi as a power of 2 cyclotomic polynomial, which is x to the n plus 1 with n a power of 2, which seems just fine as far as we know. Okay, so what do we need to know about these rings? So there are rings we can add and multiply. They are related to some deep algebraic number theory, but I won't comment on it too much during the talk. And what we also need is a notion of size of elements in the ring, and an element of the ring is small, of the ring R is small, if its coefficients have small magnitudes or small absolute values. Okay, so the coefficients of the polynomial are integers, and if these integers are small, then I consider that the ring element is small. Okay, so the first instantiation of a public key encryption scheme from algebraic lattices was from Andrew in 1996. And I want to insist on that date. So that's 25 years old. So these kind of assumptions are not really new. In particular, it's 10 years older than LWE, if you think of it. So the scheme is pretty simple. So I wanted to recall it here, just to define precisely what we are talking about. So keygen, I sample two elements, f and g small in the ring, and I define f prime to be 3f plus 1, but that's mostly like a cosmetic version of f, just to make the decryption simpler. H is a ratio of the two polynomials, mod q, and then the public key is h, and the secret key is f prime or f. Okay, then I have two versions of encryption. So the historic version, which is providing some kind of one-wayness, one-way encryption. So I sample S small and I output 3HS plus M, where M is a random input. And the INCPA version, which would be sample S and E small and output 3 times HS plus E plus the message mod Q. So in both cases, the ciphertext is just an element mod Q. And to decrypt, I multiply by f prime mod Q, and then I notice that this is small mod Q, and then I reduce mod 3, which should give me the message M. And if I also want to recover S, once I have M, it is not too difficult. Okay, so in the next few slides, I will concentrate on keygen and the one-way version of the encryption scheme. So the entry problem is related to key recovery. So in the entry problem, we are given H, which is G over F. And there are two versions of the problem. So one is the distinguishing version, where we want to distinguish G over F from uniform. And the other one is a search version, where given H, we want to recover F and G or some multiple, some small multiple of the pair FG. So this is related to a lattice, L, which is a set of pairs of elements in R square, such that FH minus G is 0 mod Q. And this object is quite rich from an algebraic perspective. So it's actually an R module of rank 2, because it's a subset of R2. And it's a subset of full rank of R2. And module means here that it's stable under addition. So if I have two pairs that satisfy this equation, the sum of the pairs also satisfies the equation. And it's stable by multiplication, by scalar multiplication by elements of R. Okay, so if I multiply a pair FG that satisfies the equation by any element of the ring, it still satisfies the equation. So it's a module, and that's exactly the definition of a module here. It's also, I mean, if you interpret the polynomials as integers, so you view a polynomial with integer coefficients as an integer, as a vector of n integers, then you are living in a subset of z to the 2n, and it's a z lattice. So it's both a module and a lattice. And it is special in the sense that it contains a very short vector, f prime and g. So if we have h, which is a ratio of f prime and g small, then this module contains an exceptionally small vector. Okay, and because it is both a module and a lattice, we call this a module lattice. Okay, so from an efficiency perspective, first, in terms of correctness, a small q suffices, and it can be quite limited. I mean, like 10, 12 bits. And the costs of all known attacks grow exponentially with the degree of the ring. And at the same time, all the user operations are quasi-linear in the degree of the ring. So that means all operations are quasi-linear in the security parameter to encrypt a linear number of bits, we pay a quasi-linear time, and so on and so forth. So it's kind of optimal in terms of asymptotic efficiency. And with practical parameters, so it's convenient because thanks to the NIST post-quantum standardization process, there have been many instantiations of these schemes. So we have like very precise figures of instantiations of untrue and other variants, other public key encryption schemes that I'm going to describe later. So it turns out that for security equivalent to breaking AES 128, the public key is around 1 kilobyte, and so is the ciphertext. So then the sizes differ because some variants use different types of assumptions, different types of noise, different types of security model, and so on. But the order of magnitude is about the same. Okay, so what do we have in terms of security? So if you want to prove security of such an untrue scheme or a variant thereof, so the one-way CPA security derives from the harness of two problems. So first, you would assume that H looks uniform, which is the untrue decision problem, and that would allow you to replace H by the H generated by keygen by a uniform H. And once H is uniform, you would assume that the function that takes S and M and outputs 3HS plus M is one way. Okay, and that looks a bit like a ring LW. So it's a variant of search ring LW. If you want to get rid of an assumption, we know how to get rid of the first one. If you take F and G of magnitude about square root Q, then I proved about 10 years ago with Ron Steinfeld that H in that case is actually statistically close to uniform. So the first assumption holds unconditionally. But there is a downside to it, in that if you try to set parameters for such a large choices of F and G, then Encrypt becomes significantly less efficient. So what do we know in terms of attacks? So there are several parameter regimes because you can choose Q, you can choose N, you can choose the magnitudes of F and G. So for Q poly and F and G like smaller than square root Q, either of the form square root Q divided by poly or F and G constant, the attacks are not much better, are either exponential in the degree or not much better than exponential in the degree. So if F and G are constant, there is an attack by Kirchner and Fook, which is adapted from the BKW algorithm, which heuristically costs exponential n over log log n. If you take a larger Q, then different things can happen if you take different F and Gs, different magnitudes for F and G. If F and G are constant, then lattice algorithms perform far better than usual. And these instances of untrue with Q large and F and G constant should be considered weak. If Q is really too large, like 2 to the square root 10, then it becomes polytime. Whereas if F and G are just below square root Q, then we don't know anything special. The best known attacks still have costs that grow like exponentially in the dimension. Okay, so let me move on to ring LWE. So search ring LWE was introduced in a paper that I co-authored at Asiacrypt 13 years ago with Ron Steinfeld, Tanaka, and Shagawa. And the problem is defined based on the distribution. So we have a secret S in RQ, and the distribution is as follows. We sample AI uniform in RQ, EI small in the ring. BI, which is AI times S plus EI in the ring, and then we output AI BI. And the problem is to recover S from arbitrarily many samples from this distribution. So it's a search problem, and it's quite related to the one when S of N-true. And in 2010, Lubashevsky, Peikert, and Regev introduced the decision version of that problem, where the goal is to distinguish between Oracle access to the DRS distribution and the uniform distribution. And they also gave like a search to decision reduction. So if you think back about N-true encrypt, search ring LW gives you the N-true encrypt one when S, whereas decision ring LW gives you the N-true encrypting distinguishability. Okay, so how can we encrypt from ring LW? So this encryption scheme is based on a general framework introduced by Lubashevsky, Palacio, and Segev in 2009. Very often in the literature, it's referred to as a Diffie-Hellman-like encryption because it's really looking like Diffie-Hellman but additive and with noise. So the key generation is to take A, B, which is minus AS plus E, where S is small, and E is small as well. So it's an instance of ring LW with a small s and small e. Then to encrypt, we glue together A and B. So it's a 2 by 1, 1 by 2 vector. And we multiply by a small t and we add some noise F. And it's exactly ring LW. It's exactly like keygen, but with a twice fatter vector and looking from the left and rather than looking from the right. So it's essentially the transpose of keygen. And to this T, AB plus F, we add in the most significant bits the message that we want to encrypt. And then decryption is essentially just a vector product, an inner product. So if we inner product C, the ciphertext with a vector S and 1, then we recover something which is Q over 2 times the message, plus some noise, plus some decryption noise, and rounding gives the message. So in terms of efficiency, so again, I mean, the best known attacks, they have costs that grow exponentially with a ring dimension. All known, all the algorithms that have to be performed by the users have costs that grow quasi-linearly with a ring dimension. So, with one step, when we encrypt a number of bits, which is linear in the ring dimension. So asymptotically, it's still very efficient. When you look at it, it looks less efficient than N-true because, in particular, the ciphertext. So now the public key has 2 elements instead of 1, and the ciphertext also has 2 elements instead of 1. So it would seem that in terms of space, it's twice worse. It's actually not the case because when you implement this, the first element of the public key, the ring element A, is only stored as the seed used to generate it. So you would sample a seed and then use a hash function to expand the seed to the element A, and that's how you would represent A. So basically, in the key, you only need to represent B, to store B. The rest is negligible, so it's almost 1 element for the key. And when you encrypt, if you look at the decryption equation, most of the bits of B are useless. So only the most significant bits, very few most significant bits are useful to get decryption correctness. So when you encrypt, you wouldn't send the full ciphertext. So you would send the full first half. But the second half, you would only send the most significant bits. So it's also almost just a ring, 1 ring element. And and if you look at instantiations provided by the NIST post-quantum standardization process, then one such instantiation of this scheme is New Hope, which gives you public key size and ciphertext size of the same order as the untrue instantiations that I mentioned earlier. So for the comparison, Frodo is about 10 times larger. So Frodo relies on LWE and not on algebraic lattices. So if you want to use non-algebraic lattices compared to those ring LWE based or untrue based schemes, then you pay essentially a factor 10. Okay, so now I want to focus on security. So ring LW is famous to have because it has a famous relationship with ideal SVP in the form of a quantum reduction from ideal SVP to both search and decision ring LW. So an ideal SVP is just the shortest vector problem for a subset of instances, where this subset corresponds to ideal lattices. So what is an ideal lattice? It's a module of rank 1. So it's a subset of R, which is stable under addition, which implies that it is a lattice. And it is also stable by scalar multiplication by elements of R. So it's you can imagine this as just like the untrue rank 2 module, but where you have only one coordinate instead of two coordinates. And here this reduction is also from worst case to average case. So meaning that if you can solve ring LWE, which is an average case problem, then you can solve any instance of ideal SVP. Okay, so I have a couple of comments. I want to comment a little on this result. So first, it's going only in one direction. So it doesn't mean that if ideal SVP was found to be easy, it doesn't mean anything on ring LWE, because you can always reduce an easy problem to a hard one. So that's in terms of attacks, if one has an attack on ideal SVP, I mean, it doesn't need to carry over to ring LWE. So that's the first observation. The second one is that in terms of setting parameters, it's not so interesting because so if you want to set parameters against the best known algorithms, the best known concrete attacks against worst case ideal SVP, then you need to figure out how to cost the best known attacks against ideal SVP, against worst case ideal SVP, which is not convenient. I mean, it's to test algorithms and to see how far they can go. It's much easier if you start from average case instances. So, in my opinion, the main value of this reduction is that ring LWE is, in a sense, general enough to capture the whole hardness that you can have in ideal SVP. So there is also a relationship to untrue, which is less known, which is of the form of a reduction from decision untrue to search ring LWE. So this reduction you can find in the survey by Chris Pikert, a decade of lattice cryptography. And I don't think it's been published anywhere else. And the reduction is quite elementary. So in particular, it shows that if you can break search ring LW, you can break untrue. So if you can break ring LW based schemes, you can also break untrue based schemes. So the reduction is as follows. So you have an H in RQ and you want to decide whether it's of the form G over F with G and F small or uniform. And so this H, what you do with it is the following. So to find out whether H is uniform or of the untrue form, you are allowed to use a search ring LW oracle. Okay, so what you do is you sample S and E small, and you create the one sample ring LW instance H times S plus E. Okay, so if H times S plus E, if H was uniform, then this is a true ring LW sample. And if H was not uniform, maybe it's not a ring LW sample. Okay, and then you send it to the ring LW oracle. If it recovers the S, then you say uniform, and else you say untrue. Okay, so first, if H is uniform, indeed, the ring LW oracle will recover S, the same S, and then the output is correct. What's more interesting to see is what happens is H is F over G or G over F with G and F small. And then you can consider the following equation. So H times S plus E can also be written as H times S plus F prime plus E minus G prime. Okay, because the F prime times H cancels out with the G prime. So that means that the S is not properly defined when you send HS plus E. So it's undetermined. So in particular, the ring LW oracle is going to have a hard time figuring out whether it was HS plus E or HS plus F plus E minus G prime or some variant of it. So with some probability, it will make a mistake. And then that means this was an untrue instance. Okay, so what do we know in terms of attacks? So for ideal SVP, for polynomial approximation factors, all known attacks still have a cost that grows exponentially in the dimension. Things become interesting from a cryptanalysis perspective when the approximation factor increases. And then we have significantly better attacks than for SVP. For untrue, when the modulus is polynomial, all attacks have costs that grow exponentially with the dimension. And if Q is larger than this and F and G are constant, then lattice algorithms perform far better than usual. For ring LW, we don't have such difficulties. So we don't have large regimes of parameters for which such degeneracies occur. And in fact, ring LW, if you try to express it as a lattice problem over R modules, the only known ways to do it result in modules of rank strictly larger than 1. So we don't know how to express ring LW as an ideal lattice problem in a way that preserves the geometry and which would make sense in terms of attacks. Okay, so now let me focus on module LW. Oh, the date is wrong. So, so it was introduced in 2012 in a paper that doesn't really focus on module LW harness. It's an article by Brakersky, Gentry, and Vaikuthanathan, which is very famous in the FHE literature. And they wanted to have a framework that captures both LWE and ring LWE. And they define what they call generalized LWE, which is actually what is known today as module LWE. So it's a generalization of both LWE and ring LWE. So it's also defined in terms of a distribution. So we have a secret S, which is not an RQ element, but a vector of RQ elements. And the distribution D of S is obtained as follows. So AI is now a vector of RQ elements. EI is a small noise in the integer ring in R. BI is AI in a product S plus EI, and then you output AI BI. Okay? And search would be find S from arbitrarily many samples from D of S. And decision consists in distinguishing between D of S and the uniform distribution. So if you take K equal 1, you recover exactly ring LW. If you take N equal 1, the degree of the ring to be 1, then you recover exactly LW. So it provides a transition between ring LW and LW. Okay, so again, we can use this design by Lubashevsky, Palacio, and Segev to encrypt from module LW. So it's very similar to what we did with ring LW a little bit earlier. So for keygen, we generate an instance of module LW. So we have a matrix A, which is generated from a seed. And then B is minus AS plus E, where both S and E are small vectors in the ring. To encrypt a message mu, which has n bits, we glue together A and B, the two elements of the public key. And we sample a module LW sample on the left in the form of T times AB plus F, plus to which we add in the most significant bits of the right-hand side the message. And then decryption is, as before, it's just an inner product between the ciphertext and a vector essentially made up of the secret key and rounding. So I have a quick remark on this scheme, especially on the date it was introduced. So if you followed the NIST discussions, there was an IP claim, intellectual property claim by the CNRS based on the patent by Gabori and Aguilar-Melchior, explaining that their patent would apply to Kyber because it looks similar, but that patent is actually older than it's not older. It was filed later than the publishing of the article by Lubashevsky, Palacio, and Segev. Okay, so in terms of sizes, so it's what you get by using module LW is quite similar as what you get with N-true and ring LW. So one instantiation based on module LW is Kyber, and then you have public key and ciphertext sizes for similar security levels that are of similar sizes. So you are still around 1 kilobyte. Okay, so what do we know about the relationship between module LW and ring LW and module lattices? So there is a typo in the title of the slide. I'm not going to talk about LW here. So ring LW reduces to module LW, and that reduction is quite elementary and results in the same modulus and the same noise rate. Then we also have a reduction from module LW to ring LW, but the ring LW modulus is higher with a similar noise rate again, and that reduction is derived from an article by Albrecht and Deo on that was published at Asiacrypt 5 years ago. So at a very high level, that means that module LW and ring LW are somewhat equivalent. If you look at concrete parameters for small modulus and reasonable noise rate, it could be that ring LW is harder than, no, it could be that module LW is harder than ring LW. There also exists a worst case to average case reduction for module LW, which by composition extends to ring LW. So from module SIVP of rank K to module LW of rank K. So that means that as soon as there are instances of module SIVP of rank K that are hard, in the worst case, then module LWE is hard on average. So it's not, So that means we can get rid of ideal lattices because we don't need to rely on modules of rank 1, ideal lattices. We can actually have harness that relies on modules of rank strictly larger than 1. And we can also express module LW as an instance of module SIVP, meaning that contrary to the reduction from ideal SVP to ring LW, so that reduction was possibly loose because we don't know how to express ring LW as an ideal SVP problem. In the case of module LW, that worst case to average case reduction at a very high level doesn't have the same looseness. In particular, module LW can be expressed as a module SIVP problem. So it's, in a way, module LW is the average case version of module SIVP. Okay, so now I'm going towards my conclusion. So I have like a summary picture. So I think this was my first scientific talk in PowerPoint, and usually I use Beamer, and then I gave up. I gave up with this slide. I tried to do it, and then that was too much. So here you have the tablet version. So yeah, so here on this picture I have like ring LW, module LW, ideal SVP, and module SIVP. So the arrows are reductions. So ideal SVP reduces both to module SIVP in the worst case domain, in the worst case range. So the top of the figure is worst case. The bottom is average case. So ideal SVP reduces to module SIVP of rank 2, which reduces to module SIVP of rank 3, and so on and so forth. So these are like almost trivial reductions. Less trivial is what goes down. So worst case to average case reduction. So ideal SVP reduces to ring LWE. Module SIVP of rank 2 reduces to module LW of rank 2. Module SIVP of rank 3 reduces to module LWE of rank 3, and so on. And you have inclusions also at the bottom. So from left to right, these are easy reductions. So ring LWE, you can plug in module LW of rank 2. You can plug in module LW of rank 3, and so on. The backwards arrows on the bottom are more difficult. So the backward arrows at the bottom, they necessitate conditions on the modulus and the noise rate. And in particular, this implies that not all of these arrows compose. So when you look at such a picture, you have to be very careful on about the small prints. And you cannot just take the arrows and compose the reductions. You have to look at the precise conditions that you need for the different parameters for the different reductions. Another comment that I want to make is that in this picture, so ideal SVP seems isolated in a way because nothing points back to ideal SVP. Whereas the rest, even if there are restrictions on parameter, all the rest is somewhat connected. So there seems to be some kind of, at least from what we know, there seems to be some kind of separation between ideal SVP and the module stuff, like the module LW, module SIVP, and ring LW. So in this picture, there is someone important who is missing, so untrue. And that's one of the problems that I find very interesting these days. So to find the precise location of untrue in the picture, so in particular, it's somewhere around the dotted line, probably, at least as far as we know. So in a work that we had with Alice Pellemari last year at Asiacrypt, we gave 2 reductions on untrue. So we showed that ideal SVP reduces to search untrue. We also showed that search untrue reduces to decision untrue, but it's another variant of search untrue. So these 2 first boxes, they don't compose. So we have relationships between ideal SVP and search and true and decision and true, but the search and trues are not exactly the same. And we also know that decision and true is no harder than search ring LW. So, which is why the conjecture that n-true is around the dotted line makes sense. It's ideal SVP is no harder than search and true, and decision and true is no harder than search ring LW. And there is a suspicion that search and true is equivalent to decision and true, even though these are not the search and trues. Another work in that direction was described yesterday by Joel, who essentially showed that, so that work essentially shows that modulo ideal SVP. So if we work with an ideal SVP oracle, n-true is essentially unique SVP for rank 2 modules. So, which is a worst case problem. So we are looking at rank 2 modules for which we have the promise that there exists something unexpectedly short in it. So again, I mean, that doesn't solve the question of where n-true lies. So it gives a worst case expression for n-true, which also lies on the dotted line. Most likely, it's somewhere between ideal SVP and module SIVP. And there are plenty of things hidden in the essentially. So the reductions also have conditions. Therefore, parameters that are very large, or the reductions are very expensive. So there is plenty of work that remains to be done in this direction to better understand the relationship between n-true and the other module problems. Another kind of question that I find interesting is the choice of the ring. So very often we choose this ring of x, which is x to the n plus 1. So it's both convenient for implementation and for analysis, because for analysis we are playing with cyclotomics of powers of degrees powers of 2. For which we know plenty of things. But what is impacted by this choice of phi? So an interesting direction is to find phis for which ring LW, ideal SVP, or n-true are easier. And as far as I know, we only have very partial results in that direction. Or find phis. So on the other side, find phis that have interesting properties for efficiency or functionality. So is x to the n plus 1 the best phi for getting smaller ciphertext? Or can we use other defining polynomials to get some special functionalities? So related to the first problem, there is this module product, middle product LWE, which is some kind of variant, another structured variant of LWE, which we do not know how to nicely express in terms of modules. So it's kind of a weird variant, which I don't describe here, but it has the following properties that it still allows for asymptotically efficient public encryption, even though in practice it's less good. And it is known to be no easier than ring LW for exponentially many phis of degree n. So it's kind of hardcore for ring LW across the choice of the defining polynomial. And this maybe can be viewed as a first step for finding a specific polynomial phi, which would be hardcore for all the polynomials, for all the rings. Because if you get a reduction from middle product LW to ring LW, so some kind of reverse reduction, if you get a reduction from middle product LW to ring LW for a specific phi, then that means that this version of ring LW for this polynomial is hard as soon as ring LW is hard for some polynomial phi. if I had to bet, I would go for power of 2 cyclotomics, but that's a very wild guess. Okay, and the last line of research that I find quite interesting in this area is to look at these possibly easier problems, ideal SVP and untrue. So they're only possibly easier because we don't know reductions in the other directions. But if we look at reasonable parameter settings, they are still very hard. So like untrue with a polynomial modulus or ideal SVP with polynomial approximation factors. As far as we know at this stage, we don't have strong attacks on these, or stronger than generic lattice attacks. So what can we do with these problems? So can we use them to do interesting things? So instead of trying to attack them, which we tried for quite some time, can we go look at the problem in the other from another angle and try to use this like possibly weaker problems to have interesting functionalities or interesting efficiency or very efficient schemes. And one recent set of results in that direction was to use the untrue assumption for FHE construction. So there was a talk on this at this Asiacrypt to use entry to get faster FHE, and a concurrent work on the same topic at CCS. So which shows that maybe these problems they have some like efficiency advantages. Okay, so it's time to conclude. So thank you for your attention. And if you have questions, I can take them now or offline.
We have plenty of time for questions. Yes.
Okay. So thanks for the talk. How would you compare the security of a ring LWE sample and a module LW sample of the same size?
So what do you mean by same size? In the same with the same overall dimension?
No, I mean the bit you need to represent them.
Yeah. Okay. So I'm trying to figure out the question because I mean it's not an easy question because representing the instance is already tricky because in a module LW instance you start with a vector of AIs. So this looks like bigger as an instance because you instead of having a single A you have a vector of A's. But all this is stored with a seed.
Yeah.
So this costs basically it costs 0 to represent at least as a fresh sample.
Yeah, just the seed, yes, indeed.
So, okay, so for you, this would have the same sizes.
Yeah.
Okay. Then I would say that module LW is
stronger.
Yeah, stronger because so if you write it as an LW instance with ring LW, you would have a secret of dimension n. But with module LW, then you have a secret of dimension n times k. Yeah, that's so it's possibly significantly harder.
Okay, thank you.
The questions? All right, then let's thank the speaker.